I'm going to be talking about the Darwin package ecosystem, tool ecosystem, and the project a bit. And I'm kind of kicking it off, and then we're going to be talking about 4 of the tools that have been developed in Darwin. So for people who haven't heard of Darwin, it's a project in Europe to build a federated network for the data analysis network for the European Medicines Agency. So we receive protocols from EMA, and we have to implement them and send them to data partners across Europe and consolidate the results and present them. And it's really high throughput in the sense that we have to do a lot of these studies. We have a short period of time, and we also need quite a bit of flexibility for each of the studies. So because of this, we've had to develop new tools, and we're going to showcase 4 of them this morning. So I'm going to start with talking about a tool that I worked on called the CDMConnector, and this is somewhat similar. When Georgina was giving her talk, I was thinking about this object relational mapping. I think this is kind of a similar idea in R, not for ETL, but for data analysis. So we connect to databases from R using DBI, the database interface, and you can use any driver that you want. You can use ODBC or JDBC, and then we have like 3 schemas that we're kind of interested in making sure that we have CDM schema, a schema in the database where you can have write access to, because pretty much all of our tools need some place to write tables to, intermediate tables, and then also Achilles, the Achilles tables, which provide like pre-computed data that we can use in the analytics. And then from that, we create this reference, the CDM reference object. And when we create this object, we do some checks to make sure that that all of the tables are there and that they have the correct names. And you don't necessarily have to have all the tables. You can select a subset of tables. But if you do add a table, then they do have to have the correct column names. And so here's an example of like where if I connect to this this database, there's missing fields in some of the tables, so we'll get an error. And these validation checks are really helpful because we kind of stop the process early on if there's an issue with the CDM. So we need some idea of what the CDM interface is, and we want to check that initially up front when we create the CDM reference object. The package provides several example data sets. These are like Eunomia data sets. So you can use them to try out examples. And so connecting to them is pretty easy. If you don't have it already downloaded, it will download. I use DuckDB quite a bit, and it works pretty well. And so this will create a connection to a DuckDB database with an OMOP CDM with 200,000 patients from Cynthia, Synthetic Health, and using the COVID-19 module. So here we create our CDM object. If you print it out, you get a kind of a list of the tables, and you can also have additional tables in the CDM object, like cohort tables or the Achilles tables, or other tables that you add. So I mentioned we like check that you have write access, we check that you have the right column, but we do these validation checks kind of upfront before we move on to any of the analytics. This just works like a list of tables. So if you're familiar with the Andromeda package in R and in Hades, it's really the same idea, but this is for a remote CDM object, like a remote OMOP CDM instance. So if you select an element of this list, it's going to be an OMOP table, and it will send a query to the database and return, in this case, just the top few rows of data. If you want to sort of characterize your data set, we have like a snapshot function that will give us just some overall information that's pulling out of the CDM metadata tables. How many people, how many observation periods, earliest, latest, the name. In Darwin, we really need the ability to write quite a lot of SQL queries against the CDM. And so we're using dplyr to write these queries because, well, I'll go into some of the advantages of using that, but we need to essentially be able to have like a lot of custom code to write queries against the CDM. And we need them to be translated to SQL, to the direct SQL dialect. So dplyr in R can do this, and it will work on a variety of database backends, as well as local data frames in R, or Parquet files on disk, or like data.table objects. So it's sort of like this nice language we can use to query CDMs that are stored in different database management systems. Currently, we're testing on 5 database systems that we're using in Darwin, and working on adding Spark support soon. Definitely the idea is to support all of the OHDSI databases and let people use whatever drivers they want. But this just requires a lot of testing and working out all of the issues with any SQL translation. So here's an example query you could run where we can look at the top, say, drug ingredients in the CDM. So this query is written in dplyr, similar to like the IBIS package that Hayden was mentioning in Python. It sends the SQL to the database, and we get our result back. If you want to take a look at the SQL that was generated, you can use the show query function, and you can see what SQL is generated. We also add helper functions to make cross-platform queries easier, and a good example of this is the quantile function, which exists in it's important for data analysis, but it's not implemented the same in all SQL dialects. So we really can't just use this function because some SQL dialects don't have it, or they implement it differently. So we have a summarize quantile function that you can use in CDMConnector that will write the correct cross-platform SQL that you need, and you can just put in, which quantiles you want to get, and it will write this query, and you can get your quantiles out that way. Here I'm just getting the year of birth grouped by gender from the person table. And here's the SQL that this generates that we don't have to write. And the way dplyr works is we can just keep piping this into more and more dplyr functions, and then that will create more and more nested subqueries. We also do cohort generation. So we build cohorts in Atlas, save them as JSON files in our study repositories, and then we want to generate them. So a nice pattern that we use is just to give them descriptive file names, put them in a folder. So here I have 2 JSON files from Atlas, COVID-19 and type 2 diabetes, from the OHDSI phenotype library. And we can use read cohort set and point it to that folder, and then we get like a data frame that has the cohort names and the automatically assigned IDs. If you want to control the names and IDs with like a metadata file, you can do that as well. But if you don't have them, we'll just automatically assign IDs. And then you can pass that into generate cohort set, and this will generate the cohort. So hopefully everyone's familiar with sort of the overall cohort structure, cohort table structure. This is really fundamental to OHDSI and all of our analytics. We have cohort definition ID, subject ID, start date, and end date. And so this is how we can translate those definitions from Atlas into a cohort table. And this cohort table is it's a table in the database, but it also is an object in R, and so it has some additional attributes and metadata associated with it. So we can look at the cohort counts. So even though like the type 2 diabetes didn't have any patients, this is still included in the metadata. So we have the number of records and number of subjects. Settings for the cohort object include just the name, and then the attrition. We have like an attrition table you can get. And we're also thinking about generic functions that can work across many of the tools. So something like settings could work with the cohort objects, but also like result objects that we have for our analytics. We also have the need oftentimes to generate a lot of cohorts that are relatively simple. So they don't have like a lot of inclusion criteria, but they're really just like based on concept sets. And so this function here, generate concept cohort set, it essentially does any Atlas cohort definition that only includes that top box of like your inclusion, your initial criteria. So you can pass in a list of concept sets and then additional criteria if you want to use the first one, required observation pre or post index, when to do the end date, how you want to do the exit criteria. And so this will generate a set of cohorts. And what's nice about it is it's one SQL query that gets executed to generate this. So it's quite a lot faster than if you were to have, if you were to do this in Atlas and then generate all the SQL and do them one by one. You can transform the CDM. So this is something we thought about where you could subset an entire CDM to a set of patients or maybe just patients in a particular cohort. So this is a way to just transform a large CDM into a smaller CDM. And so that's what this function does, where we have initially 213,000 people in our CDM. And once we subset to this one cohort, then if we query the CDM anywhere in our code later on, then we'll only be getting those people that were in the cohort. And we're not copying all of the data. We're just essentially adding joins onto all of the tables. So if you ever query any of the tables, there's going to be a join that happens before that, where we'll just subset down to the cohort table. You can flatten a CDM. So the CDM is just essentially a bunch of observations. We split them into domains in the database, but really what we have is just a whole bunch of observations and that are timestamped. So if you want to just get this all into a single table, kind of like the profile view in Atlas, that's what this function does. And so I've had people ask me about doing something like this. And so CDM flatten will just give you one table back, and you generally wouldn't want to do this with the whole CDM, but if you subset down to a smaller group of patients, this can be quite nice. You can save a CDM as CSV, Parquet, or DuckDB. So if you want to just pull your CDM out of the database and put it on disk, this is how you could do this. And we can also like subset the table. So in this case, just to keep things small, I took out the vocab tables and then saved them as Parquet files on disk. And then you can read them back into R from there. And again, probably not your whole CDM, but if you had a smaller CDM, this would be nice. And then another kind of experimental function is just being able to copy a CDM from one database system to another. So if you want to move the CDM from DuckDB into Postgres, you can use the CDM copy to function where I just create my Postgres connection. And then again, just to speed things up, I remove the vocab tables and then copy the CDM to Postgres. And then disconnect, you can just use the DBI function to disconnect from the database. So I went over some of the functionality in the CDMConnector package, but it's really about building the CDM object. And then this object gets passed to downstream analytic packages. And so you'll see a few of those now, kind of how we use this as the foundation for later analytics. Okay, so I'm going to stop sharing and pass this on to Mike to talk about patient profiles.
Oh, hi, my name is Mike, and I'm a health data scientist that's been working on Darwin for the past 2 years. So today I'm going to give you a short software demo on a package that we developed called PatientProfile. And it has a hash sticker, pink. Then like the main objective of this package is to do 2 things. Like the first is to add like patient-related characteristics to like a cohort table that you created using CDMConnector, and also to identify like the intersection between like any cohort tables, concept table, and also like clinical or mod related table within the CDM object. And to do that, we created like 4 groups of different functions to achieve those 2 scopes. Like we have like a group of functions that do the add demographic. So then also depends of what intersect information you want. We have like function related to cohort and concept and also tables. So now I'm going to go over like within each group of function what actually it does. So within add demographics, we have function called datasex, and what it does is like based on the person ID or the subject ID of your cohort table, it found the like gender information for each of the patient inside your cohort. And to do that, it's really simple. All you have to do is like pipe in the datasex function, and what it does is return this sex column that indicate the gender for each of your patient in your cohort. And also within this function, it has argument that the user can use to define like the column name and also what to do with the missing values. And then we have a function called addAge. What it does is based on your cohort subject ID or person ID, it calculates the age for each of the patient in your cohort. And the way it calculates the age in this function is based on this index date, where the user have to specify the date that this function used to calculate the cohort. By default, it always used the cohort start date. And what it does after you pipe it onto your cohort table, it will return you a column called age with the age of each of the patients. And also within this function, it has the ability to do age group by using the age group argument. What it does is take a list of the age group that you want, and it will return you like this age group column for your cohort tables. And also with the age group function, you can like specify your own label, so you don't have to use the default name if you don't want to. Like for example, what I did here, I created like an extra age group column called a category, and I label everyone under 17 kids and everyone over 18 adults. And then we also have a function called add prior observation, which what it does is like for each of the patient within your cohort table, it goes into the observation period table and look at how many days of prior observation that person has inside its own the current observation period. So this diagram demonstrates how this function calculates the observations. So it will look, the user has to specify like an index date. Then what it does, it look at like how many days of prior observation each of these person has. So all you have to do to calculate that is use this function, pipe it onto your cohort, and it will return you a column with patient prior observation in numbers of days. And also within this function, it has an argument called prior observation type. So if you don't want your prior observation information in numbers of days, it can return like the observation start date instead. So what you have to do is change this to date, and it will create a column called start observation, which will give you your observation start date for that patient. And also we have a function called add future observation, which does very similar thing to prior observation, but instead of give you the prior observation in number of days, it gives you like the future observation in number of days for each of the patient inside your cohort tables. So it works exactly the same as all other function inside this package. All you have to do is pipe it onto your cohort table that you created using CDMConnector, and what it does, it returns you an extra column with your future observations. Then we also have a function called add in observations. Then what it does is for each of the individual inside your cohort, it generates like a binary flag that indicate whether this person for this date, this person inside an observation period. So it works same as or other function inside this package. All you have to do is pipe it on, and it will give you like a column that indicate whether this person for this date, whether they are inside observation. Okay. And also this function has a window argument. So what you can do, the user, is like give it a list of different time window, and it will tell you whether this person are inside observations for those time windows. So what I done here, I did a time window for 20 years, 40 years, and 60 years. And what it does, it gives you 3 extra columns. And each one is like an indication flag of whether this person are still in observation in 20 years, 40 years, or 60 years time. And notice there's also like a complete interval argument here. Like what it does is if you set this to true, this person would have to be in interval inside observation for the whole time window, like to be able to get a 1 in the flag. If you set it to false, it will give you like an 1 indicator if it's inside observation anytime inside this time windows. And then we also have a function called a date of birth. Really simple. What it does is just give you the date of birth of each of your patient inside your cohort tables. So it will give you a column called date of birth with the birth date of these people. And that's everything inside a demographic. So we also have a function called as a demographic. Basically, what it does is if you pipe it onto your cohort, by default, it gives you the age, sex, prior observation, and future observations. And within this demographic functions, we have different arguments that allow users to turn off the information that they don't want. So in here, this example, I set the sex equal to both. So instead of returning you everything, it will take the sex column out. So now I'm going to go on like the intersection function inside this package. So like this is related to the second scope of this package, which is to return the intersection information between a cohort table and any other table inside your CDM object. So for all the intersection function, it has 3 different arguments related to like your origin table. So like this is usually the cohort table that you want to do the intersection from. So it has like it has an index date. So this is like the date that you want to use to calculate the intersection. Then it has a window argument where the user can specify a list of like time window that you want like the intersection to happen. And also it has like a sensor date argument, which like the user can use that to specify like the end of the follow period that they want the intersection to finish. And then depend of what table you're doing your intersection for, it has different arguments. So if you're doing like an intersection between a cohort table, your cohort table with another cohort table, there's argument where the user can specify the name of the other cohort table you want the intersection for within your CDM object, and also like there's a target cohort ID argument where the user can specify like what cohort inside that cohort table that you want to do the intersections. And also like there's a target start date argument where the user just specify like the date for that cohort table where they use to calculate the intersections. And like if you're doing an intersection between like your own cohort table and a concept set, like it has an argument called concept set where the user can give it a list of concept ID and it will return the intersection information between your cohort table and those concepts. And also if you do it, you want the intersection information between your cohort table and other clinical table within your CDM object. We have function called add table intersection where there's an argument called table name where you specify what like the name of the table that you want to do the intersection for. So, and also like there's an option where the user can specify like what like intersection information they want to return. So there's like a flag. So you can return like a flag, which is just an indicator of whether like there's an intersection between those 2 tables. Like there's a count, which kind of like the number of like intersection that exists between those 2 tables. Then there's the date where the user can use it to return like the date of when that intersection happens. And also like there's the days where the user can use it to return like the time difference between like your index date and also like the date of when that intersection happened and number of days as an integer. And for the date and the days estimates, there's an extra argument for those, which is called the order. So for the order argument, it can take either first or last. So if you set it to first, it will return you like the first intersection date that happened in your target cohort. If you set it to last, it will return like the date of your last intersection. Okay, so to do all that, in the end, we created like 12 different functions, which depends on what you want to achieve. It will give you the information. So I'm going to give you a few examples. So for example, if you want to get the flag, the intersection flag between two cohort tables, you would use this function called add cohort intersect flag. So what I did here, I said I want to get the intersection flag between my cohort table and also this other cohort table that exists in the CDM object called drugs. And the window I'm interested in is like these two, like I want the intersection to happen anytime after 1 to 180 days, and also anytime after 181 days to 365 days. All you have to do is type this on, and for each of the cohort inside this drugs table, we will get a column that indicate whether the intersection happened between those two tables. And we're going to get a column for each cohort and also each time window. So which indicate the intersections. So also, if you want to get the intersection between like your cohort table and also the exposure tables, you can use the add table intersect function. And here I use the count, so it will return like the count of number of different intersections that happen between those two tables. And here I specify the windows to like 0 to 365 days. So what it does, it will return you a column that gives you the count of number of intersection within that windows. And then if you want to return the date of the intersection between two cohorts, you could use the add cohort intersect date. So what it does is, instead of like give you it will give you like the exact date of when that intersection happened. And then like this example give you like, if you want the intersection between your cohort and also like a concept list, you can use add concept intersect. So what you have to do is like give it a concept list in here, and it will return you like the number of days between the like every concept ID within like your concept set and your cohort tables. Okay, so that's everything. Thanks for listening, and also thank you for all the contributors that contributed to this package. Now I'm going to pass it on to Martí, and he's going to tell you about cohort characteristics.
Yeah, so well, good morning, good afternoon, or good night, everyone. Like, I'm Martí Català. I'm a senior data scientist working here in the University of Oxford, and one of the DARWIN EU developers. So I'm going to present CohortCharacteristics, which is a package built on top of like CDMConnector and PatientProfiles, the two packages that Adam and Mike kindly presented now. You will see that many of the parts that I'm going to present are going to be familiar. So yeah, here we have our nice hex sticker. Thanks, Marta, for that. And yeah, a little bit like the workflow of the package. Basically, the package has 3 types of functions. We have what we call summarize functions. All of them, you're going to see that it's like very repetitive. They start with summarize something, and these functions produce like a standardized output that we call summarize result that summarizes something. Basically, if we say summarize cohort attrition, it's going to be like the standardized output containing like the cohort attrition or large-scale characterization. We are going to see like 7 examples in today's presentation. Then we have like the plot functions. These functions work with the output of the summarize, and it creates plots, as they can see, and it works with like this object that we call summarize result. And basically now currently it only supports ggplot, but we are also working to support plotly, and let's see if we have more ideas. And then similar to plot, we have another kind of functions that are like the table ones. They're going to be table wherever, and like it works always with the output of summarize, and they produce tables. And currently we have implementation for GT and flex tables, but also we'll consider other applications in the future. So yeah, basically it's like first the summarize function and then like the plot or table function. So what I'm going to present today is like the 7 summarize functions that we have that are like summarize cohort count, summarize cohort attrition, characteristics, large scale characteristics, cohort overlap, and cohort timing. And then like each one of them has an associated table and plot function. So just we're going to start with the easier ones. Like just to note, in this presentation, I'm using Eunomia as a data set and like several cohorts that I've built. I'm skipping the part of the code to create the cohorts, but everything it has been done with like the functions and Adam presented before. Happy if like someone has more doubts or something to help to regenerate all the plots that I'm going to show. So yeah, basically when we create a cohort, for example, in this case, I created like a cohort that contains like 6 conditions. We have like this metadata that we store in settings that Adam was saying, that it's like myocardial infarction, fracture, allergy, infection, pneumonia, and asthma. We have like these 6 conditions. And in the metadata, one thing that we also store is like the number of cohorts. So we know how many records and how many subjects we have in each one of these condition cohorts. And what we can do is we have like this function called summarize cohort count that basically exports this information that we had here in like this standard summarize result format. This, as it's the first time that probably most of the people sees it, like this is our current standard format. It contains 13 columns. First, we have like a result ID that's like just an identifier. Then we have like a CDM name that's like the name of the database that like was used to create this cohort. Then we have like different aggregations. For example, we have group name and group level, strata name and strata level, then variable name, and also it can contain a variable level. Like also in parallel, we can have like additional name and levels for all that are not used in this package, but in other packages are needed. And finally, we have like the estimate, where we store like the estimate name, the type, and the estimate value. If any of you is interested to know more about this standardized result that we use, it's defined in OMAP generics, and we have some vignettes on that. But just like as we go through the presentation, we are going to see many times this like 13 columns standardized result, and I wanted to mention it. So basically, once we export this once we export this metadata, we can like pipe it, and we use like table cohort count, and we can build this nice GT in this case function that like allows us, for example, if here we we would have like more, it would be a network study with more databases. We could like put each one of the databases one side to each other, or if we want, like we have some customizing options, like if you want to compare CDM names, or if you want to compare like cohort names or different options. Similarly, we have another function called summarized cohort attrition. Again, like attrition is part of the metadata in our cohort objects. We have, I'm going to work with this simple example that like it started with like initial events of viral pharyngitis, and then like we did like a first step to restrict to only adults, then a second step to restrict to only females, and then we defined the study period that goes from 1970 to 2000 as its eunomia. And then like we have this nice attrition table, but again, we have a function to export it in this standardized result format that basically like what it's useful having this standardized result format is that later we can use this plot cohort attrition function with like many PIs love it, because with this we can plot a nice cohort attrition, and we know how many individuals and records are we losing in each one of the steps, and we can like the output is like a diagrammer diagram that can be exported as PNG, PDF, or whatever image format that we want. Then like probably the one that it's the most important package of a function of the package, and probably why this package exists, it's called summarized characteristics. Basically, this function is used to create like standard tables once. So basically I have my cohort, it's the one that I presented before, I showed before. I created like a new column saying period, that it says like if the cohort start date was in the 70s, 80s, or 90s, just to have some example of a stratification. And then what we can do is like we specify different things that we want can export. So I'm going to through all of them. So demographics basically like exports the demographics function. Age group, we can add like some age groups to characterize. We can like stratify by different columns that our cohort table has. And then this should be familiar for all of you, as like Mike was presented before. So table intersect count, you can present like the number of visits prior year, you say in which window are you interested, and then we are going to have a variable that is like number of visits prior year. And same way, we've defined some conditions in the conditions table. We've seen them before. We are interested to know how many conditions, which were the conditions anytime prior. We are interested like in a binary value variables to know yes or no for each one of the individuals, because at the end we want like a percentage of individuals who had it. And then we define a window, and exactly the same for medications, but in this case we are interested just in the year prior. So yeah, like if you go through the documentation, and so like we have nice vignettes and it's easy to use, I think. And then like the output, it's as we've seen across all the presentation, it's like a summarized result format. And then the nice thing is that we can build these like GT tables here, like would be the default one, where we say, okay, we want just headers by the different strata. So we have like one column for the overall cohort, but then another one for those records in the 70s, another one for those records in the 80s, and another one for those records in the 90s. And for them, we have like the different things. So as you can see, like all these 4 rows that are like cohort start date, cohort end date, sex, age, are like what we were pointing before, saying if we want demographics true or false. And later we are going to see like the other variables. So I've created like a more customized one, like that was like the default one. But if you want to specify, we can specify, okay, we want to format the counts and the percentage in this way. We want to join the interquartile range in this way. And we want to exclude some columns because, like, for example, in this, like in this case that we are using CDM name, we are only using like eunomia, so like we are not interested to see the CDM name or compare them. Like with this, we can have like a nicer version, and then we have like what we were saying before, right? So we have like the cohort start date with the different ranges and medians, the same for cohort end date. We have like the percentage of sex, as if you remember in the attrition, we're restricted to only females, so everyone like, well, we have 100% of records that are females. Here we have like also median and information about the age group, prior information. These are like the percentage of the conditions that we pointed before. So when we set like condition anytime prior, we have like in this window, so then they appear here. And this is number of visits that everyone like it's set to 0 because it's eunomia, but in other databases usually it's useful. So the nice thing and why we have like some PIs that love it is that this table, it's very nice because it's like HTML format. So we can show it in Shiny apps, we can show it in Quarto documents, in Quarto presentations and so, but also you can export it directly to Word. So what I'm just showing now, like you can like just save it with the GT save function, and it creates like a Word document with your table formatted nicely. And like the idea is that you don't need much customization to have like a final table one for your paper. So this is a nice functionality that, well, a lot of people like. And then continuing with the presentation, we have like another function called summarize large scale characterization, that basically you define some windows that you are interested. In this case, we define a window that is like anytime prior, and another window that is like anytime after, and you define like some tables that you want to characterize. In this case, I'm going to characterize condition occurrence and drug exposure. As you can see, we have 2 arguments to point to the tables that we want to characterize. So event in window refers to tables that we are only interested to see incident events. We only care about of the start date. This is usually the case of conditions. We care about like if they had it or not, in that they had an incident condition occurrence in that window. Whereas for drug exposures, usually we are more interested if they had like an ongoing record. And this is what episode in window is used for. So yeah, we have these 2 arguments to point to the condition, like regarding if we are interested with incident counts or just over like ongoing counts. And then again, output, we have like this 13 column format. There's like the summary result. Again, like the nice thing of this is the functions that are built on top, that are like the table and plot function. Let's go first through table large scale characteristics. So we have like the number of counts that each one of these conditions were recorded in each one of these windows. In this case, like for like, so I can fit it in the presentation. I restricted to just the 10% of top concepts, but here we could have like 100%, like the top 100 or all of them, and then we would see like all the different counts. And here, like, well, as expected, we see that like as its first record of viral pharyngitis, so no one had a record anytime prior, but some of them like have repeated events, and well, we could see which were the most recorded conditions in the different windows that we were working. Similarly, we can use like the plot large scale characteristics. In this case, what I'm going to use, it's like I'm going to use the 2 windows and characterize them. Here we have like many concepts. That's why we are going to use another visualization later. But here we can see each row is one of the concepts. And like we have in red, the percentage for like any time prior, and in blue, the percentage for any time after. So we can compare the characterization of the different concepts and see, well, whatever we are looking, if we see interesting stuff that we want to report, or depending on what's our goal. And similarly, we can use like plot compare large scale characteristics, where we define like a reference, that in this case is going to be the records of any time prior, and then we plot them. So each one of these points is a concept that, well, this is like a plotly, this is something that we are working on, but then you can see like it's an interactive plot where we can see each one of the concepts, like which is like the reference is like the percentage of individuals who had it anytime prior, and the comparator is like in percentage anytime after. So this one would be like what we saw before, the viral pharyngitis, and like we can like see different interesting concepts. Continuing with the last two functions, we have this one is called summarize cohort overlap. I'm going to define like 4 cohorts of sinusitis, one for bacterial sinusitis, one for viral sinusitis, another one for chronic sinusitis, and one that it includes any of the 3 prior sinusitis. And we are going to see like how these 4 columns overlap. For example, we expect that this cohort called any sinusitis contains all the other ones. So again, it's just calling summarize cohort overlap with our cohort. Output is like this summarize standard object, and we can pipe and use the table overlap. So what we see, for example, if we compare like any sinusitis and bacterial sinusitis, we see that like 70% of the records are only in the any sinusitis cohort. Like we have 30% that are in the bacterial sinusitis, and we have no record only in the comparator cohort, as these 3 zeros were expected as any sinusitis contains the definition of the others. And in the same way, if we have like table cohort overlap, like at this stage, I guess that everyone can guess that there exists a function called plot cohort overlap, that what it does is like to plot, okay, it's not sure, to plot the overlap between the different cohorts. So last function, and with this I'm going to finish, we have the summarize cohort timing, use it to characterize like the timing between 2 cohorts. In this example, I used like 3 different drugs, acetaminophen, morphine, and warfarin, and I've instantiated them in a eunomia. And then what you can do is like summarize cohort timing to these cohorts. We have an option to restrict it to only the first entry, but you could decide not to do it. In this example, I decided to do it so the results were like easily to interpret. And then again, the output is a standardized result format. And then we can have, as we've seen across all the presentation, the table cohort timing, where we can, like, for example, choose like the time scale that by default it's days, but as we are going to see, numbers are quite big, so we are going to like use years, and then you can like choose things like decimals, exclude some columns. And so if someone wants to play with the package, we are happy to receive feedback, and like we are open to change things if it's needed. So yeah, here we can see if we compare like acetaminophen and morphine, we know that there are like 35 individuals who have like both. So they transition from acetamin to morphine or from morphine to acetaminophen. And if we look at the timing, we see that it goes from like minus 31, 34 days they started like acetaminophen till like 77, years that it happened morphine. And that the median is like that they start morphine after acetaminophen. And well, and we could like go to the interpretation on it, of each one. And similarly, if we have table cohort timing, we have plot cohort timing to do nice plots. For this, we have 2 modes. First, like the standard one with like box plots, and then it's just a visualization of what we were saying what we were seeing here. So we have like just a nice visualization of the same. We could see that like morphine comes after acetaminophen, warfarin comes like way after acetaminophen, and then warfarin usually comes like after morphine, but sometimes it can come before. And we also have like another type of plot. It's like the density plot, where we can like plot exactly the same, but instead of like a box plot, we can plot like these density plots that are like nicer to get an idea, because I think that box plots are good summaries, but like with the density plot you can get like a better idea, and basically we see exactly the same that we were saying with the box plot, but with a nicer shapes and so. So yeah, just to finish, CohortCharacteristics is on CRAN, so you can install it from CRAN. We have like a first viable version there. It's built on top of all these functions that we were mentioning, PatientProfiles and CDMConnector. You can also install all our development version, which we are working on currently. We have like the documentation with the link that I shared in the chat. So if someone wants to go through all our documentation, we have like the reference, like where all of our functions, as well, you've seen it, summarize, table, and plot functions. And then we have like vignettes for each one of our functions, explaining how they work and how to use the different parameters. So yeah, with this, I'm done. Just thank you everyone who helped to contribute to this package, especially like Nuria did a lot of work with all the table functions, and Mimi and Marta did like a lot of work also on all the plotting functions and so. And with this, I finished my presentation. I'm going to hand over to Kim, which we hope that she's still awake, as for her it's past midnight and she's connecting from Korea. So yeah, if you are alive, the floor is yours, Kim.
Okay. I'm alive, yeah. I hope you can see my screen. Hi everyone. My name's Kim. I am a DPhil student at the University of Oxford and also a developer for DARWIN. I am going to present CohortSurvival, which is a package that also is built upon some of the functions that have been presented today. And it's maybe a little bit more epi-oriented. It's more like a self-contained package. It was started because we had the need to do survival studies. So the intention of the package is to be able to perform descriptive survival analysis. It's basically a wrap-up around our package survival, which if any of you has ever done any survival analysis, you'll definitely know. And it just makes it a little bit easier to work with the package with OMOP data. And it's, as I said, it's basically designed to perform descriptive survival. So the main functions of this package retrieve survival estimates to create Kaplan-Meier curves for both cases when we have one outcome of interest, so a single event, or competing risks. And then there's some extra functions, but mainly the objective of the package is this one. As all our packages, it is available on CRAN, and there is a website where you can find more information and also the source code if you want. For this demo, I'm going to use a mock data set that's created from the MGOS2 survival data set from the package survival. So it's just retrieved from there and then restructured into OMOP format and into the CDM. And this mock data set has the target cohort of people diagnosed with MGOS. And this main target cohort also has some extra variables like age, sex, age group, and spike, etc., which I will use later on for some stratification examples. And then this mock data set has two outcomes that I'm going to work with. One of them is progression to multiple myeloma, and the other one is death. And just a little insight, there's also a function in CohortSurvival called generate death cohort set that basically creates a death cohort from the death table for any given target cohort. If the user does not have a death cohort per se, then they can use this function to create it. So for descriptive survival, there's a lot of different things that one can do, but mainly we're interested in a group of people who are a target cohort who have whatever diagnosis or whatever condition, and then they might develop another outcome. So we have a main outcome that we're interested in studying the survival for. And in this case, there is a function in the package called estimate single event survival, which only requires the CDM object and then the name of the target cohort table and the outcome cohort table of interest. I'm also putting here follow-up days just because then the plot looks nicer, but this is really not necessary. And then you can check this in the GitHub, but there's a lot of different inputs that these function also allows. Things like if we might be interested in requiring a minimum number of survival days, or if we want to follow up people for a specific number of days, or we might want to censor on a particular day, things like that. There's a lot of different parameters that can be tuned, but the only required ones are these three. So the CDM, the target cohort table, and the outcome cohort table. And the output of these estimation function is of the summarized result format that Martí was explaining before. So this is a format that we use across all our packages. And there are two inbuilt functions in the package that help visualize the results. One of them is plot survival, which basically just plots the information. There's a couple of things that one can tune, but the most important thing maybe is you might want the race table underneath or not. And then if the user wants, they can plot the cumulative failure probability instead. And then the other visualization tool is stable survival, which retrieves the survival summary. So this is very important when you are reporting survival analysis in papers. And this function retrieves median survival if it's a single event, analysis of restricted mean survival, and then survival estimates for any times given. And it retrieves it for any cohort. So in this case, it's just single event and no strata, so we have only one row, but we would have multiple rows if we were to be interested in different events or if we had different stratification. We'll see that later. And there's other things that the package also extracts. I'm not going to get into detail, but we have you can get all the number of events and people at risk, and then also the iteration for the study. You can also get the participants with another function. Yeah, all of these you can check later in the GitHub if you're interested. And another nice thing that this function does is that it allows for stratification of the results. So for any columns that exist in the table cohort, you can stratify by them. So in this case, in the MGUS diagnosis cohort, I had age group and sex. So I can ask for stratification for each of them separately or together. And any other variable that I can add as a column can be used for stratification. So the output looks the same, but then when we plot, we can facet and color by the different strata groups and names. And we can also focus on just one of the strata levels and plot the risk table underneath. So in this case, I'm plotting these single event survival for the age groups, for the different age groups, and the overall population. And in this case, when we retrieve the summary, we get a row for each of the strata. So we get the overall summary statistics, but also for the different age groups, sexes, and both of them together. Now, that was for a single event, but sometimes when you are estimating survival, you might be interested in competing risk. The idea is that sometimes you have a main outcome of interest, but there might be another outcome that competes with your outcome, in the sense that if your target population has that competing outcome, they cannot have your main one. So they're both competing. And then the way you are estimating probabilities change. So for instance, in this case, if our main outcome of interest is progression to multiple myeloma, we might be interested in, well, we probably should use a competing outcome of death, because if people die, they cannot progress. So in this case, we can use the function estimate competing risk survival, which is in CohortSurvival, and it requires the user to specify these the three cohorts, which should be in the CDM. And again, the output looks like it usually does for all our packages, and we can use plot survival to plot the two outcomes, the progression and death cohort in this case. And when we retrieve the summary, we get one for each of them. And similarly, we can also stratify. In this case, I stratified by age group here, and then the plot is stratified also by both the outcome and the age group, and we get one row per cohort of interest in the survival summary. And finally, so those are the main functions of the package, the ones that are inbuilt in a way. Sometimes when you're doing a survival study, you are interested in modeling data. CohortSurvival does not have inbuilt modeling functions, but there are many functions for modeling survival analysis in survival packages or in CMP-RSK, which is for competing risks. The only thing is that you need the input to be in a particular format. So we have some functions in CohortSurvival that allow the user to get the target cohort in the format necessary to then model. So for instance, we can use at CohortSurvival to add these necessary cohort survival data to our target cohort, which basically is a status and a time variables. And then the output of these function, of this adding these two columns, can be fed into a normal call to, for instance, a Cox proportional model fitting from survival. And similarly, we can use another function of the package called add competing risk cohort survival, which adds the same type of information, but in the case of competing risks. And these can be fitted into some modeling function, for instance, from this package that models that feeds a fine and gray model. These first lines here are just because this function needs all the variables to be numeric, so I had to change sex to binary. But it's quite straightforward anyway. And finally, just wanted to give a final example on another way, kind of different way maybe to use this package. I'm using Eunomia here, so I'm connecting to the Eunomia CDM using CDMConnector, and then I'm using the package drug utilization, which is another package created in the DARWIN EU interface that helps do studies around drug usage. And then with this package, I create a cohort of people who are prescribed acetaminophen. As you can see here, this cohort has roughly 14,000 records and around 2,600 subjects. And if we call the estimating of event survival function with this cohort both as target and outcome, but using the cohort end date as the outcome variable, then we're basically following these people that get prescribed this drug up until they stop getting it. So this is basically a drug discontinuation study. I'm here also forcing some event gaps so that I get more time points for the risk table. And then again, we can plot that, and then we get the risk table underneath, and we can retrieve the survival summary for the specified times. And yeah, this is a team effort. So obviously, it's thanks to all the people who also worked in this package. Thank you for your attention. And if you have any questions, you can reach any of us, or you can check our GitHub.
Really nice, Kim. Thank you. Thanks, Marty and Mike. Are there any questions for any of us about the Darwin tools? If not, maybe it's time for a break.
Yeah, Adam, thank you so much for that presentation. I'm hoping that those demonstrations were fantastic. It's like you're assembling a nice R book, that we can now for how to teach some of this material even. So I am super hopeful to see more examples coming forward too. All right, at this time, Votek, did you have a comment or a question?
Yeah, so I know maybe we want to go for break, but my question is, you showed some examples on demo data. I wonder, this is the first glimpse I got into any of the Darwin stuff. I was wondering if since they might be ordered by EMA, can one see those packages being used on a more, not a toy study, but actually a real study? And maybe this was presented earlier, but are there examples besides, vignette style, kind of a complete study because you probably developed these packages because you needed them for, all these studies. So you didn't really develop just to show them on a toy scenario.
Go ahead, Ed. Unmute yourself first.
I'm not presenting, but I am co-leading Darwin development. So maybe I'll jump in just on that point because it's actually a very timely one. So with the Darwin project at the moment, the current status is like all the tools are open source in that they're public on GitHub and on CRAN. The studies, of which we've already done a number, at the moment, the code is not made public for the studies we've already conducted, but that's actually well, I don't want to promise, but it's pretty much sorted that it's all going to be made public imminently. It's just, let's say, a bit of back and forth between different lawyers on the different licenses that might be applied to that study code. The study reports themselves, like what we submit to the EMA, are also made public, like through the EMA website. So like the current status is the reports that we submit and the packages themselves are all public. But just to say that the studies with high likelihood, just a few last things to sort out, should also be made public in probably the next coming months as well. And then obviously, like when we publish papers with for the different Darwin studies as well, like the code for those studies will be like in the publication, like linked in the publication and everything. So very much hopefully fitting with the OHDSI ethos.
Yeah, because the motivation behind my question, I actually brought it up on the Hades and Strategus people who are developing that. If one can basically package it as that all the dependencies would be available, you could plug it into some of the other OHDSI infrastructure, and once you have done all the hard work of making your data OMOP, the carrot could be, oh, and why don't you just run all the Darwin studies now just to check it out? So that is the motivation why I'm asking.
Yeah. So that's a very good point, actually. And I think there's like a few things to consider. The first of all being we are entirely in Darwin based around OMOP, but we are kind of centralized in that we have a subset of data partners who are mapped to OMOP. Primarily based in Europe, right? And we run our studies normally in around 5 data partners. And so things like phenotyping for that study will have been done specifically for those 5 data partners. So as and when code is made available, for sure, people can try and run it. But you should still think about whether the transportability of that study code will work for your data, because there might be some kind of specifics to the data partners we have, just in terms of the phenotyping and things like that, that might mean if you want to expand it more than anything, you might have to just really reconsider about whether the phenotypes used in that study can then be also applied with yours. So that's probably the caveat, but obviously, hopefully, like with all the packages being public and also the study code, it should make it relatively easy. Hopefully, I understood all the presentations, but obviously I'm much more involved in the project. But hopefully that code will directly work on your CDM instance. It's more about the research question and the context of your data that you'll have to think about to then understand if the results are different to ones you see in Darwin or are just slightly unexpected. There might be like a number of explanations. That's probably like a bit out of what we can support from Darwin itself.